Okay, so let's take a look at the next little set. I'm planning on taking a look at probably numbers 9, 10, and 11 on this particular section. And these are solving problems that are rational equations and rational inequalities. So let's see what happens here. So in this first question, number 9, we have these two fractions being added together and set equal to a third fraction. So the first thing that we want to do is I'm going to go ahead and rewrite them so I have a little bit more space to play with. And I'm also going to go ahead and factor this denominator so that it makes it a little bit easier to handle. And the first thing that we should really notice pretty quickly is that we're in a situation where we have common denominators throughout this problem. So what I'm going to do is I'm going to multiply each piece of this problem by x plus 2 and x minus 3. So I'm going to distribute both of those binomial factors through all three of these pieces. A lot of teachers are going to refer to that as our fraction buster. Now you're going to notice that these are going to cancel here. The x minus 3's are going to cancel. And right here, not only is the x plus 2, but also the x minus 3 is going to cancel. So when we're all said and done, what we're down to is x minus 3 times x in the first piece. There is an x plus 2 times a 5 in the second piece, and all that's left in the third is 25. Now, this is kind of a quadratic that's left over, and kind of an obnoxious one at that, because we do need to clean it up a little bit. So I've got x squared minus 3x in the front half. I've got a 5x plus 10 in the second, and of course, it's still equal to 25. So a little bit of combination of like terms leads me to x squared plus 2x, and I'm going to go ahead and slide that 25 across, because one of the things about quadratics is we can either factor them, we could complete the square, or we could do the quadratic formula. But remember, factoring is always the easiest trick, and 5 and 3 have a product of negative 15 and a sum of 2, so that was pretty fast. So right off the bat, I see that my answers are 3 that's going to make it happen, as well as negative 5. But there's a little hint in this problem that is often given. Hey, it says make sure to check for those extraneous solutions. And when we look at this problem, if we looked back at the beginning, if I were to plug in x equals 3, that would lead me to divide by 0, which is something we're not ever able to do. So I have to reject that answer, because if I look back, I can't divide by 0 to create my solution. So as it turns out, x equals 5 is my only answer in this particular story. Now, notice from number 9 to number 10, it changed not equal to 0, which again, it wasn't equal to 0 to start with, but we got it there. This one is an inequality. So the first thing that I personally like to do is to get the problems into factored form. And now what I want to know is, when is the problem actually positive? Well, positive actually is very closely related to the number 0. So I know negative 3 would be equal to 0, and that's actually a good answer, which is why I'm putting that solid dot there. Negative 2 and positive 2, although they produce a 0, those are both zeros in the bottom of the problem, which means we're not allowed to do that, because we can never divide by 0. Now, kind of polish it up, if you will, I personally like to just kind of guess and check around. And if I picked a number out here like 5 or 10 or something, I would get a positive on top, because 5 plus 3 is positive. 5 plus 2 is positive. 5 minus 2 is also positive. And that quotient of positives is always going to be positive. And if you look at what we want, that's exactly what we want. Now in here, a simple number like 0 would lead me to a positive on top. 0 plus 3 is positive. 0 plus 2 is also positive, but that's a minus on 0 minus 2. We can't be inside here, because the positive divided by the negative is going to be negative, and that's not what we want. Now, if we continue the process, try negative 2.5, we'd have a positive here. Negative 2.5 is going to be 2 negatives, and as it turns out, that's actually a good value as well, because 2 negatives do make a positive. And in the far left region, all three of those terms are going to be negative, so we can't be there, which means my inequality is going to be x as an element of from -3 to -2 or from 2 to infinity. Anything in these regions is going to yield an inequality value that has a positive value. Now, going a little bit further here, we could do a little more with x plus 2 and x minus 3. Just like the previous question, I'm going to seek out the number 0, and 0 clearly happens at 3, and 0 happens at -2. Those both appear to be good numbers. However, there's something that's kind of sketchy here, because I have a square root, and so at 3/2, which is right in here, I can't have that because that would divide by 0, but there's something else at play. I cannot go this way at all, because if I try to pick any number that is below that 3/2, that's going to be a problem because I'm going to end up taking the square root of a negative. So really the only part of the problem that I can even consider about the inequality is over here. So let's go ahead and finish that up. And if we tried a number, say above 3, like 6, I would get a positive times a positive over the square root of a positive, which is definitively positive. But this doesn't want positive. I want negative answers. I want values below 0. And of course, if we slide in here and try a number like 2, I'd get a positive, a negative, and the square root of a positive. And that is, in fact, okay for the domain, but it's negative, which is what I wanted. So my answer for x is x would be an element of anything from 3/2 to 3. Or if you wanted to, you could say x is between 3/2 and 3 if you wanted to use inequality notation instead. All right, just a little bit further to go. We're going to find a few asymptotes here. Now, in these problems, I guess I'll just take it from the get-go here. X equals -3 is clearly going to be a vertical asymptote because that's where the denominator would go to 0. I'm going to do quick synthetic division, and I know that we haven't done a lot of this, but one of the tricks that we learned in class is the remainder portion that we have here, we're just going to go ahead and throw it away, which means we have a slant or an oblique asymptote at x minus 6. Please notice that you may never, ever, ever have an oblique asymptote and a horizontal asymptote. This is called an end behavior, and you cannot be simultaneously horizontal and slanted. You're going to be one or the other. So again, notice I did that. I could keep going, but we're going to throw that last value away anyway. One thing that can be helpful to do, kind of looking to see where I put my calculator down, and I don't have this one pre-set up, so it's just going to take me a second to do that. But if I go ahead and I type in my problem, which was x squared minus 3x minus 7 over x plus 3, and I go ahead and I type in x minus 6, that's my asymptote. Now remember, that's an end behavior asymptote, so that's what should happen out on the left. I'm going to hit a zoom 6 because I don't really know what this graph looks like. But here comes the original graph, and here comes my asymptote, and you notice it's getting very, very close. Now I can see that the left side of the graph, I'm not seeing it, so that's not a problem. I'm just going to open my window up a little bit, and it looks like it's kind of going down. So let's see if I can get it. So there's, oh, there it is. There's the left side and the right side, and here comes the asymptote. And if you put your finger right over the top, the two graphs actually look very, very similar everywhere on the ends, just not in the middle. So that kind of confirms my end behavior asymptote, and you could see the vertical asymptote right here at x equals -3. Now in letter B, it's a little bit faster because x minus 3 times x plus 2. Neither of these is a common factor of the numerator. We sometimes want to watch out for removable discontinuities, but this one does not have one. So we have vertical asymptotes at x equals 3 and x equals -2. And we have a horizontal. Now this time we don't have a slant asymptote. Over here it was a second degree over a first degree, which left a first, but now the bottom is larger in terms of its power than the numerator. That always leads us to y equals 0. Okay, letter C is kind of the booger of the bunch. When we look at it, we can see that x equals 2 vertical asymptote pretty quickly. But a third degree divided by a first degree should be a second degree. So again, I'm going to go through here. And as long as this doesn't divide in perfectly, it's going to be an asymptote. But I know 2 does not go into 7, so I know it can't go in perfectly. Our rational roots theorem says that's not possible. So remember, I'm going to throw that out. That means my parabolic asymptote is going to look like this. Now again, not totally set up in advance to do that, so I'm kind of doing it the way you would on a test. Take 2x to the third minus x squared plus 4x minus 7 divided by x minus 2. Again, please feel free to pause if you are having a little bit of difficulty keeping up with this, but I'm just going to go ahead and put the asymptote as the second one. This should be an upsloping parabola. I haven't really changed my window from the previous problem. I'm hoping it's actually good. I'm not even seeing much right there. So clearly I don't have a very good window. So let me try that again. I'm going to hit my window and let's just go -10 to 10. And in fact, this one I could kind of tell that most of the action was higher than what I was looking at. So here comes my original graph. That's not the asymptote, that's the original graph, and here comes the asymptote. And you can tell that there's a little bit of my original graph that I did not see. So even though I went up to 50, it wasn't high enough. So let's try that one more time. So here comes the original graph, and we'll see a little piece of it right here, and here comes the asymptote cruising right on through just like that. And notice again, if you covered up the middle, the two graphs, the graph and the asymptote look awfully similar. In fact, my finger's too thick. Even right there, they look almost identical. And last but not least, our final story is if we can factor this one right here to x plus, I guess this is going to be a 3 and a 1 like this. Neither one of those divide into the numerator. Rational roots theorem says only 1 and 7. That's not going to include either one of these. So I have vertical asymptotes at x equals -1/2 and x equals -3. And over here, because of the fact that the powers are actually matching, then our horizontal is at y equals +1/2. These would be very easy to check and rationalize and make sure that you did it well by plotting them in Desmos and making these dotted. You would see confirmation that you would do well. So that's kind of the end of that story, and I think we're doing all right. So that's the end. Unfortunately, yet again, my dumb screen has hijacked and gone over to my throw projector, which is off right now. So that's the end of the video. I was able to get it to stop. See you soon.